It says, write the net ionic equation for the cell reaction and calculate the value of the electromotive standard reduction. Oh, yeah, okay, whatever that is, right? For the NiCad battery. Well, that is not terribly well stated to us. In fact, we're probably going to end up doing a search on the internet to find out what equations are they talking about? What is happening inside of a nickel cadmium battery? Well, when we do that, we will go find out that one of the things that's happening inside is that cadmium hydroxide, which is a solid, is picking up some electrons so that it can turn into cadmium as a solid and 2 hydroxide in an aqueous solution. And we have to remember now that we're interested in these standard reduction potentials, negative 0.81 volts. The other equation that is happening is for the nickel oxide hydroxide. Water as a liquid and an electron is going to turn into nickel completely hydroxide. Okay, that looks a little more normal as a solid. And hydroxide again, aqueous. And it also has a potential associated with it, 0.52 volts. Okay, they're wanting the net ionic equation for this. Well, this makes me have to think about how is this going to work? Well, I know for the cell, it should be the one for the cathode minus the one for the anode. And I said that the way that I did this is I picked for the cathode the one that was more positive. Well, that would be this one. The 0.52, this one is goes with the cathode. So I can say that this is the cathode, and that means red cats, so this is the reduction. That means this one's going to be the oxidation, and this is the anode. And then I'm going to subtract the one that happened at the anode. So I'm subtracting the negative 0.81, which means that overall I'm going to get 1.33 volts out of a NiCad battery. Now what else do I have to do to this? Well, then now that I've identified which is which, I can switch one of them because they're both listed in the books in the in the tables in the back as reduction potentials. Well, this one I was actually using as a reduction potential, so I will keep it in the order that it already is. This one I identified as needing to be the oxidation, and what I've written down here is the standard reduction for it. So this one needs to be flipped, and when you flip it, that's why the sign change happens here. Okay, so but I need to flip this one. So let me flip it. I'll write cadmium as a solid first, and then the hydroxide ion that's with it. Okay, that's everything that was over here, becoming the cadmium hydroxide and 2 electrons. So I flipped it. This one is in the correct order. However, I noticed that if I'm going to combine it with this, it only has 1 electron here and not 2. So I'm going to need to double all of this. Remember, this is doubling how much? It's not doubling this voltage. So I'm going to double this. I'm going to have 2. This weird stuff here. And 2 waters. And 2 electrons. And then it will become 2 of the nickel hydroxide. And 2 of the OH minus aqueous. Now if I look at that, I will notice that not only do I get to cancel out the electrons, but I'm also getting to cancel out the hydroxide. And now I can write down the overall equation, that it's cadmium as a solid interacting with this strange nickel compound, which is also a solid. That's a little weird, but they've got water there to help things move around. So, okay, we got water. That takes care of everything on the left. This is going to go over to what's left on the right then. Cadmium hydroxide as a solid, and the nickel hydroxide also as a solid. Barely managed to get that on there. That's our overall, that's our net ionic equation.